I've already resubmitted.
Okay, you've got to turn. You got to turn this bolt, and you have a choice of which wrench you want to use. It's a pretty bad bolt, but you get the idea. And then you can use the blue wrench.
Blue.
Okay, or you can use the red wrench.
It's going to be around mechanical.
Hang on, let me do one other thing with this. Which one are you going to use?
The one that exists.
Red.
Red?
Wait, what's the point?
Wait, what are you asking me?
Which one is going to be a better wrench to use?
The red one.
Turning it? The red one, yeah. You're just turning it, right?
Mm-hmm. Try to turn it.
Yeah,
It doesn't matter which way, you know?
I think the blue one, but because it looks weird.
No, the red,
Most
like,
wrenches are like the blue one.
Mhm.
But
Like
I
the
think the
red
red one will be better.
I feel like
Think it's
you
gonna be
know,
better?
The red
The blue
one,
one
how
will
it
be
has
better,
like a
yeah.
shorter, you know, like.
Okay, I'm going to let you answer your own question here, but let's
It
talk
depends
about.
which way you're,
I've never seen it with-
twisting it.
I
Because
like
if you're
the red.
twisting it this way, the red one will just get in the way. If you twist it this way.
So the red one, you would grab it like that.
Yeah.
Oh, well then no, I say blue.
Say blue? Okay, well you guys can decide. Maybe you'll decide in a second.
But then
So-
like, I think like not the wrench, but the thing.
Yeah, I know.
What are they called where they're like this?
She just said, I think that the random is might be.
The what now?
The tools that are like, what are they called? Never mind, I forgot the name. I can't remember.
I'm kind of curious what you're talking about. You'll think of it.
Blue is definitely better. We have come to a conclusion.
Yeah, like, you don't use them to twist bolts, but like.
Like a socket set, you mean?
Goodness gracious.
No? You'll think of it. Okay, so what we're talking about, the topic of the day is torque, or buying trucks. Okay, so you gotta know how to buy trucks. Yeah, you gotta spell it that way for buying trucks. So I don't really like the way this book necessarily is organized, but I guess I can kind of see why this comes up now. I mean, we'll probably talk more about it later. I want you to think about something though. I think I mentioned this at the start of the year. You can break up mechanics, right? Mechanics is the study of how motion is produced. Accelerations are produced by forces, right? Okay. You can break it up into two different groups. We could talk about linear land stuff or Engelvania stuff, right? In linear land, we're going to measure translational things. We're going to measure the stuff that we've generally talked about. We're going to measure position. We're going to measure velocities. We're going to deal with accelerations, and we're going to deal with forces. Forces are what cause accelerations, right? In Engelvania, you could deal with the rotational analogs of all those things, and the equations are essentially identical. Which is really cool. The relationships among the Engelvania quantities within that group, their relationship to each other is the very same as the relationship between all the stuff we've talked about, the linear land quantities and their interrelationships. So instead of position, we would talk about angular position. So instead of an object moving from point A to point B, like let's just say my displacement is 3 meters, we would talk about an angular position. Here's my initial angular position, here's my final angular position. So my angular displacement was pi over 2 radians, right? Or 90 degrees if you want to use degrees, okay? Instead of talking about walking at a pace of 1 meter per second, I would talk about maybe twisting at a rate of, say, pi halves radians per second. That's my angular speed instead of my linear speed, or my angular velocity instead of my linear velocity. If I want to talk about increasing my velocity at a rate of 1 meter per second squared, that's my acceleration, I would increase my angular velocity at a rate of, I don't know, like pi over 6 radians per second, or pi over 6 radians per second squared. So I start to twist faster and faster, right? Now, what causes linear accelerations? Forces, right? F equals ma. What causes angular accelerations?
Torque.
Torque.
Oh.
So torque is the Angulvania equivalent of a force. Okay? Torques impart angular acceleration, but torque's a little bit different. Torque is a little bit more complicated to calculate, just a little bit. It actually turns out that it's really not if you use the proper angular quantities, but we're not really doing that yet. We're not talking about angular velocities and angular accelerations yet. So we're sort of stuck with linear stuff. And if you are, torques are a little bit harder to deal with. If we're gonna turn a wrench, right, this language changes from textbook to textbook. I can remember talking about this in terms of lever arms and effective lever arms, but in this book, we're going to call this the length of the tool that we're using, the lever, and the lever arm is what I'm about to describe. So when we're going to turn this bolt with this wrench, we push on the wrench, only we're going to have to push in a specific direction, right?
Mm-hmm.
The handle is built a specific way for us to use the tool in pretty much the best way. But what if we applied a force like through a different direction? Say I'm going to push on this thing with that force vector, so pushing in that direction, okay? Well, notice that if I extend that force vector, if I extend in both directions the force vector to include a line, then that line is called the line of force. Okay, it extends infinitely far. So the extension of the vector is the line of force. The perpendicular distance from the fulcrum, the center of the thing that I'm turning, to the line of force is what we call the lever arm. Okay? And torque is really it's just going to be force times lever arm. Okay? Well, how do we calculate the lever arm then? If we say that the length of the lever is R and the length of the lever arm is L, and theta is going to be defined as the angle between the line of force and the lever. Okay, does that make sense?
Mm-hmm.
Why?
Why is it? I thought, wouldn't it be between the line of force and R? Maybe not.
It is,
Okay,
right.
okay.
R stands for the lever.
Oh.
Yeah. Okay, lever arm is L,
Mhm.
right? Okay, so then what's the SOHCAHTOA relationship that relates R to L? Sine, isn't it, right? Everybody agree? So we could say sine theta equals opposite, which is L, divided by hypotenuse, which is R, right? So then if I multiply each side by R, the lever arm is really just equal to R sine theta. So what's the best angle to push at? Say it again. What angle? What angle should theta be? What's the best angle to push at? 90, right? Because the sine of 90 is 1. The sine of any other angle is less than 1, right? Okay? And so we get the longest lever arm and therefore the most torque, because remember, torque, and that's just a capital tau, that's capital, it's a Greek T, that's what we use for torque. Torque is just equal to R times lever arm, so it's, excuse me, force times lever arm, right? So it's F times R sine theta. So for a given amount of applied force, I'm doing that right. When I'm twisting the wrench, that's my, I'm applying force to the wrench. I get the most bang for my buck. In other words, I get the longest lever arm by pushing at a 90-degree angle. At 90 degrees, the lever arm is just as long as the actual lever. But if I push at any other angle, I'm effectively shortening the lever, right? If I push straight on, how long is the lever arm? 0, because then I'm pushing at an angle of 0, and the sine of 0 is 0. So I get no twisting force. Torque is like twisting force. I get no twisting force by pushing in this direction, and we all know that. It wouldn't turn it at all, would it? Right? Okay. So does that make sense?
So you don't want to grab it at 90 degrees. You just want to push it at 90 degrees.
Right. So I mean, and that's why you grab the handle like this and push. Right? Does that make sense?
Yeah.
Okay. How could you
So blue is better.
say that? See if you can come up with a practical solution here. Let's say that I couldn't get this, I couldn't budge this bolt. It's really stuck. What can I do? What could I do?
You have put gunpowder in there.
But I don't want to. I want to be able to put it back on eventually.
Okay.
Get a longer wrench.
Get a longer wrench.
Why?
Why do I get a longer wrench?
The
Because
bigger and better.
yeah, well, in this case it is, right? Because if I get a longer wrench, right, a longer lever arm, I'm going to push it 90, right? So I already know that sine theta is going to be 1, right, no matter what wrench I use. But I get more torque. I get more twisting force for a longer wrench,
Interesting.
right? And so if you have you don't own a longer wrench, but you have like a piece of pipe, you could just put a piece of pipe over the wrench and push on the pipe then, right?
Yeah.
Okay, something like that, right? Get the idea?
That would have been helpful this summer.
Would that have been helpful?
Yeah.
Yeah, the longer the
Can I
wrench,
get my tire?
the more torque you get. Question? Deshaun?
Oh, no, it's just-
Oh, okay. Right.
Wrench.
Okay, so how does this apply then to buying a truck?
Yeah.
Now, what are the units of torque? Let's look at this. Standard units. Torque is built from the product of force times R sine theta. Well, what are the units of sine theta? Nothing, right? It's just a number. So that one doesn't provide any units. I end up then with the units of force times the units of length.
So, force is kilogram.
Force is a kilogram meter per second squared, which we call a Newton, right?
Yeah,
And then length would be
whatever.
a meter, right? If we're gonna use standard units. So a Newton meter,
Weird.
a Newton times a meter, which we would call a Newton meter, is the standard unit of torque. Now, when you buy a truck, what do they always measure torque in?
I've never bought a truck.
Never need to buy a truck.
We
And
all drive cars.
Okay, have you ever heard people talk about torque? And usually they measure in foot-pounds.
oh.
Foot-pounds of torque.
No, never heard of
Okay, dorky, customary English units. But those are the same kinds of units, aren't they? A foot-pound is a unit of length times a unit of force. A pound is a unit of force, right?
it.
We'd measure our weight in pounds, and that's gravitational force.
Yeah.
Right, so a foot-pound, it's a bad unit, but we can see that it measures a torque.
Okay.
So why is that such a big deal? Why, I mean, when you're buying a truck, typically, if you're gonna, why would you wanna have a truck with lots of torque?
You could get things.
Okay, because you can go up a hill like towing something a lot of times, right? It's usually for people that want to tow big trailers or big boats or something, they want to have a truck with lots of torque. Why?
Yeah.
Okay, well, where does the torque come from? The torque is produced by the engine, right? What does an engine do? An engine just twists a drive shaft, right? So it's providing a twisting force to the drive shaft. That drive shaft travels down, probably through some bends and travels down to the axle. And then at the axle, there's a universal joint that turns this kind of twist into this kind of twist, right? So you're twisting it this way and it's transitioning that into a twist of the axle, right? Get the idea? Okay, so the engine is providing that torque. The torque is twisting the axle, and then we're just going to attach a tire to the axle, and that's what sits us on the ground. That allows us to push on the ground, and the ground pushes us forward, right? Okay, so the torque is a product of the engine. Now, how much force is applied to the ground? Well, if I want to see what the applied force is, we're kind of working in reverse this time, aren't we? Previously, in the last example, we were trying to generate the torque by applying a force. But we could reverse that and say, okay, we want to apply a torque to generate some force out here at the end of the lever, right? Like if you wanted to catapult something, for example, you're going to want to generate some force out here to push on the projectile so you can accelerate the projectile so it'll go down range, right? Well, how are you going to do that? You're going to have to torque the whole thing, provide a twisting force down here, so you're going to twist this lever up and throw the projectile, right? Okay, more likely, you're probably where you use the torque the most is when you're driving a car. When you're driving a car, you're going to twist the axle in the car, and then that's going to apply a force to the ground that pushes the ground backwards and you forward, right? That makes sense?
Mm-hmm.
So we want to maybe algebraically manipulate this equation, and we want to isolate F this time, not T. We want to see for a given amount of torque, how much force can we apply to the ground? Okay, well then I would just divide both sides by R sine theta. So the applied force here would just end up being torque divided by R sine theta, right? Okay, now what's the radius stand for? Or the R is the lever, right? The length of the lever. For a tire, think of a tire as having a whole bunch of spokes that extend clear out to the edge of the tire,
Yeah.
right? If I have a whole bunch of these spokes, then at any one moment, only one of those spokes is in contact with the ground and the other ones are useless, right? This is the only one that's actually touching the ground, right? And so that's the one that's applying the force. That's the lever. A little bit later, this one's going to roll down there and it's going to be the lever, and this one's going to be useless, right? Well, for a tire, a tire is a continuous band of material, of rubber. So how many effective spokes are there?
None. Wait.
Well, I mean,
All infinite.
it'd be like, say it again? Well, it'd be like having an infinite number of spokes, right? Because there's never a gap between spokes. The rubber's always in contact with the ground, right? But you get the idea. So whatever part of the tire is in contact with the ground, the line between the contact point and the axle at that moment really acts as the lever, doesn't it? So it's the same thing as saying the radius of the tire, right? That make sense? Tires are pretty standard, right? So when you buy a truck, you're going to put a standard tire on it, right? So why is it then that given that the tire is, largely out of your control, that's something that just comes with tires, why is it so important to have lots of torque?
Make it go fast.
Well, what's it?
Stronger.
Okay, you're able to provide more force to the ground, aren't you?
Can't
Right.
you get bigger tires though? Wouldn't that help?
Okay, so you help you pull more?
Yeah.
Okay, so if I get bigger tires, R is going to get bigger. What's that going to do? That's bad. Yeah. If I get bigger tires, it actually means I get less torque, right? So these guys that have these big trucks that have huge tires on them, a lot of times, if you know your physics, you just kind of, that's not saying it works, right? That's not really helping. If you want to be able to pull, actually it does something. It does something different. It robs you of torque, but I suppose it probably gives you more clearance.
But then why would tractors have to?
Well, if you wanna go muddy, you need more surface.
Okay, so there's reasons people do that. I'm just kind of joking. The reasons people would want those big tires, but it really does remove you lose torque, right? Because you can't. How could you generate torque? Well, you could change the transmission so the gear ratio is different, but that's pretty hard to do. Usually when you buy a truck, you're not going to go mess with the transmission, right? You're going to leave the gears alone and maybe change the tires. If you want to actually be able to pull with more torque, you want to get smaller tires, not bigger tires, right? Now the disadvantage of smaller tires is, for a given engine speed, one circumference, so one revolution is not gonna take you as far down the road, is it? So you're gonna get less speed and probably less fuel efficiency, right? So that's why trucks, they sort of compromise and have just a standard size tire, and you build the gears to give you the best possible, combination of all things, right? But if you're gonna buy a truck for pulling, it's gonna be one that's built to give you lots of torque. That's why they're more expensive. They have bigger engines, thicker couplings, so you can't break things when you're twisting them really hard. That make sense?
Yeah.
Okay. All right, so then, that's really it. Why are diesels so good at pulling? You've always heard diesels are good at pulling. Well, it's not really that they're necessarily better at pulling. It's just that they can provide more torque at lower RPMs. So you don't have to rev your engine up to get lots of torque. Because a lot of times when are you trying to pull something, when are you applying the most force to it? Well, like you're trying to pull your boat out of the water, right? You're at rest and you're gonna be going at slow speeds and you wanna be able to pull really hard to get that boat pulled out of the water. Once you're traveling down the road, you may be gonna go up a hill, right? You don't wanna have to shift down and run your car at really high RPMs. It's hard on the transmission, right? It heats things up. So you want a diesel, you don't have to do that. Diesel, even when the engine's turning relatively slowly, it can still provide lots of twisting force to the axle. It's just and that's just a byproduct. There's good physics there. If you just compare the two different types of combustion processes in a gas engine compared to a diesel is literally called a diesel cycle. It's dieseling is what it's doing, and it's really high compression. And we'll maybe talk more about that at the end of the year if we get a chance. There's so many things we could talk about. We could do this all day long for a year and just never run out of things to talk about. But there's torque. So now if you can go buy a truck, you know what you're doing, right?
Yeah.
If you're going to be pulling lots of stuff,
So
you got to
we
get.
want foot-pound, more foot-pound.
You want more foot-pounds if you're pulling stuff, right? And you want more foot-pounds for lower RPMs, right? That's why people get diesel trucks.
Then you have to go fill up at a special gas station.
You just got to go to the green one.
Yeah.
Yeah.
They have those at like every
They
single.
only
Yeah.
have one.
It's really hard to find that
There's
diesel
like
stuff.
Six gas and one diesel. That'd be such a